complex numbers. Practically, a complex number is a sum or addition of a real number and a pure imaginary number. The standard form. What is the standard form of any complex number? That is A plus IB, where A, B both are real numbers. A and B both are real numbers. Now, important part is here. When B is equal to 0, it is not a complex number. Why? Because we have A, that is real, B, that is real, I, that is imaginary. So IB is a pure imaginary number. Okay, but when B is equal to 0, that means A plus I into 0 is equal to A. Originally not a complex number, it's a real number. So that's why B must not be equal to 0. Okay, so in that complete case, when we are writing, that is A plus IB, that A is called the real part and that IB is called the imaginary part. Okay, suppose a complex number is written in that way. Z is equal to A plus IB. That real part can also be written in that way. RE of Z, that is the real number, the complex number, Z is equal to A, and the IM for imaginary of Z is equal to IB. In that way also we can describe the real part and the imaginary part of any complex numbers. Okay, so next one, what are the properties of complex numbers? A real number cannot be equal to imaginary number. Any real number cannot be equal to the imaginary number. Let A, B, where A is not equal to 0, B is not equal to 0, be numbers such that A is equal to IB. Here look, A is the real part, B is the IB is the imaginary part. But we are here to prove a real number cannot be equal to an imaginary number. So we are here thinking about that the real number A is now the imaginary number IB. So in that case, we are squaring both. So A square is equal to IB whole square. Just writing here, that is squaring both sides. Okay, so that one is now becoming like that. X square is equal to I square B square, or A square is equal to minus B square. Okay, or we can write A square plus B square is equal to 0. And that implies always when we have A square plus B square is equal to 0 for any number of real numbers, that means A is equal to 0, B is equal to 0. But look at the thinking or the hypothesis that A is not equal to 0 and B is not equal to 0. That means here we can write this contradicts the hypothesis that A is not equal to 0, B is not equal to 0. Since the contradiction arises, since the contradiction arises by assuming that A is equal to IB, therefore, simply we can say, therefore, A is not equal to IB. So that means any real number cannot be equal to imaginary number. Okay. So next property that is also very important. That is A plus IB is equal to 0. If A is equal to 0 and B is equal to 0. Let's check any complex number is 0 if and only if. Now, if and only if can also be written in a single word, I double F. Okay. If and only if its real part is 0 and imaginary part is also 0. And imaginary part is also 0. So here, what is the proof? Practically, we have to prove that particular thing. Okay. So let A plus IB is equal to 0. Here we are thinking. So that means A is equal to minus IB. The plus IB from the left hand side has been taken on the right hand side. Okay. Now squaring both sides. We are squaring both sides. So here A square is equal to minus IB whole square, or that is A square is equal to minus B square, or A square plus B square is equal to 0, which is only possible when A is equal to 0, B is equal to 0. So just look at the theorem or the property. We have to prove A plus IB is equal to 0 if A is equal to 0 and B is equal to 0. In words, we can write it, any complex number is 0 if and only if, that means if I double F, its real part is 0 and imaginary part is also 0. And that is proved here. We have taken the complex number A plus IB as 0, and that is always or only possible if we have A equal to 0 and B equal to 0. Next one part, property, two complex numbers are equal when their real parts are equal and their imaginary parts are equal. That is, we have to prove originally A plus IB is equal to X plus IY. Already said we are writing that if and only if, in that way, if and only if a is equal to x, that means the real part with the real part, and the imaginary part with the imaginary part. That means here, that one means IB is equal to IY, which gives us B is equal to Y. So that is the first part, that is the second part. Let's prove it. So how to? A plus IB is given as X plus IY. Just write down the right hand side from the right hand to left hand. That means A plus IB minus X plus IY is equal to 0. Or we are writing here A minus X plus B minus Y into I, or I into B, is equal to 0. And which is only possible when we have A minus X is equal to 0 and B minus Y is equal to 0. So that proves A is equal to X and B is equal to Y. So that means whatever we have to prove here, two complex numbers are equal when their real parts are equal and their imaginary parts are equal. So in that way, we can prove that. Final one, property. Okay, no property. We are just proceeding with some example. Like, suppose the question is like, find the values of X and Y if given 2X plus 4IY is equal to minus I cube X minus Y plus 3, like that. Okay, so we are writing it here once again. That means 2X plus 4IY is equal to minus I cube X minus Y plus 3. And that one as minus of I3 can be written as I square into I into X minus Y plus 3. Now look, minus of that one is the minus 1, because I square means I into X minus Y plus 3. So minus of minus is now plus. So only I into X minus Y plus 3. So real part is equal to real part, imaginary part is equal to imaginary part. So write down just one line. By the property of complex numbers, we have, look at the real part, that one portion is the real part, minus Y plus 3, that one is the real part. Okay, we are writing it for your easiness like that, minus 1 minus Y plus 3 plus I into X. So that would be the real part, that would be the imaginary part. In that way, you can proceed. So here we are writing the first one, 2X is equal to minus Y plus 3, and another one part, that is 4IY is equal to IX, where we are dividing the I, so we can write 4Y is equal to x. Now that is the equation number 1, that is the equation number 2, where we have two equations of x and y. Suppose like 2x plus y is equal to 3. That is equation 1, and from equation 2, x minus 4y is equal to 0. That is equation 2. So we are writing here 2x, 2 into, that means 8y, write down, that one is equal to 0. So 2x, that one is the equation 2. Just from here, find out the value, subtract it, we are getting x as 0, eliminating 0 here. So that one was minus, so that is becoming plus. On plus 9y is equal to 3, or from here we can get y is equal to 3 by 9 or 1 by 3. So that is the first one we have found, y is equal to 1 by 3. And from the second one, 2 into x plus 1 by 3 is equal to 3, or 2x is equal to 3 minus 1 by 3, or here we have 3, 9 minus 1, 8 by 3, 2x is equal to 8 by 3, which can be written as 4 by 3. So x is equal to 4 by 3, y is equal to 1 by 3. That is the solution from that particular problem. Okay, just for the final thing, the complex number here, suppose z is equal to x plus iy, is defined by the ordered pair, that means x comma y of the real numbers x and y. That means every complex number can be written in the standard form, that is a plus ib, where a and b or x and y are the real numbers. So a plus ib is never equal to b plus ia. Okay, so ordered pair means ki we are taking the real part and we are taking the imaginary part. So that complex number can be written as the ordered pair of the real numbers AB. Why ordered? Ordered pair, already from the set theory. Ordered pair, that means which one is in the first, the order is there. Second one is the different. So in that case, AB is never equal to B comma A. Okay, that's why two complex numbers are different, and why that ordered pair definition is important for any type of complex number, because from that particular ordered pair we should proceed to another one very important geometrical term of complex numbers, that is called the argand plane. That is called the argand plane, or the complex plane. Sometimes it is also called as the Gaussian plane or the Gauss plane. So argand plane or the complex plane or the Gauss plane or the Gaussian plane. Okay, so our ordered pair means always, that's a very important in complex number. So suppose we have 7 comma 8, so it can be written as 7 plus 8. It is represented in the complex number system. Suppose 11 comma minus 4, that means it can be written as 11 plus minus 4 into I, or 11 minus 4i. So all are different. Suppose 98 plus I root 3. So it can be written as 98 comma root 3. Or suppose given I minus 15. So it can be written as minus 15 plus 1 into I, or the ordered pair is minus 15 comma 1. So in that way we can proceed with the ordered pairs in complex number, which is giving us the eigenplane or the Gaussian plane, complex plane.